Hello. So today what we're going to be talking about is something called concavity. So up until now, we've been learning about ways to use the first derivative to analyze functions. So before we learned about that, we learned about a higher order derivative called the second derivative. And now we're going to learn a way to use the second derivative to analyze a function a little bit further to get a larger picture of what the graph of a function would look like. So we're talking about this thing called concavity. So a function f of x is said to be concave up on an interval if f prime of x, or the first derivative, is increasing on the interval. So we know to find out if something is increasing or decreasing, we take the derivative of something. So if we want to know where the first derivative is increasing, we want to know where its derivative is positive. So in other words, a function is going to be concave up if the second derivative is positive. So if f double prime of x is greater than 0. And then it's the opposite for concave down. So a function f of x is going to be concave down on an interval if its first derivative is decreasing on the interval, or in other words, if its second derivative is less than 0. So you might be saying, what does concavity look like? What are we really talking about? Well, for concavity, I kind of like to think of it as being either a cup or an upside down cup. Whoops, didn't mean to extend the page there. So concavity for concave up, which sometimes I like to abbreviate as C up, so that way it looks like the word cup, a concave up function might look something like this, or something like this, anything like that. So in other words, you want to look for something that if you poured water into it, it would hold the water instead of it just dumping straight up. So in other words, it kind of has the shape of a cup. And then we have the opposite for something that looks concave down, which I usually abbreviate as C down, just so I don't have to write out the word concave every time. And it's going to look something like this. So in other words, if you tried to put water into the curve, it would slide right off. It would fall right out of the cup because it's upside down. So it's basically you just want to think about if the function would hold water or not at that interval. And when we get to the section in your book called curve sketching, where we put all of this information together onto a graph, I'll show you the different types of ways that functions can be increasing and either concave up or concave down, or decreasing and concave up and concave down. Okay, so another important definition to know that goes along with concavity and the second derivative is that of an inflection point. So an inflection point is where there's a change in the concavity. So just like we learned about that there is a minimum or maximum when the first derivative changed signs, we're going to look for when the second derivative changes signs as well. So inflection points, this is really important to note, is that they only happen when the second derivative is either equal to 0 or undefined. So in other words, the inflection points are the critical values of the second derivative. So those critical numbers that we always want to look for. So we want to first find out where our second derivative is going to be either equal to 0 or undefined, set up another sign chart just like we did with the first derivative for increasing and decreasing intervals, and then look to see if there are any changes in the concavity happening at those different critical numbers. So let's put this all together. So let's find the open intervals where this function is concave up and concave down, and then let's determine if it has any inflection points. So the first thing to do in order to find concavity is to find the second derivative. In order to find the second derivative, we need to find the first derivative. So the first derivative of this is really easy to find since we just have to use our power rule. Bring that exponent of a 3 down, it'll cancel with the 1/3, and we're going to get x squared minus 1. And then taking our second derivative, we're going to get derivative of x squared is 2x minus 0, or just 2x. So now we want to set the second derivative equal to 0, and then solve it. So in other words, we're going to set 2x equal to 0. Dividing both sides by 2, we're just going to get that x is equal to 0. So this is a critical number of our second derivative. And we don't have to worry about the second derivative ever being undefined because it's equal to 2x, which is a polynomial, and polynomials are continuous everywhere. So just like we were doing before, to find the intervals for increasing and decreasing, we're going to set up what's called a sign chart. except this time on the top is going to be our second derivative, and on the bottom is going to be our x's. So again, we're going to put all of our critical values or critical numbers onto the chart. So we only have one at 0, which we knew the second derivative was a 0 there, so we'll put a 0 above it. And then we want to pick test values on either side of 0. So how about we pick -1 for the left and +1 for the right. And then just like last time when we were figuring out the sign of the first derivative by plugging the green test values back into the first derivative, we're going to do the same thing now, but we're going to plug -1 and +1 into the second derivative and see what their signs are. So f double prime of -1 is just 2 times -1, which is -2, so we can put a negative sign above the -1. And then the second derivative of +1 is just 2 times 1, which is a +2, so we can put a plus sign above that. So now just like when we were doing the increasing and decreasing problems, all that's left is to write our intervals. So we're concave up when we're to the right of 0 because that's where our positive sign is. So we can write that interval as going from 0 to positive infinity since there are no other critical numbers that would stop it from changing. And then we are concave down to the left of 0 where that negative sign is, and since there are no other critical values, it's all the way to the down from 0 to negative infinity, so we can write that interval as negative infinity to 0. We want to make sure to remember that these are open intervals because the concavity at 0 is 0, so we don't want to put brackets on it, and you never want to put a bracket on it at infinity since it's not a number, it's more of a concept, so it's never actually included in something, it's always an open parenthesis. And then the problem also asks us to find if there were any inflection points, which I sometimes abbreviate as inf points. So inflection points we said happen when there's a change in the inflection. So we can see that there is a change because here we're going from negative to positive at x equaling 0, which means that x equaling 0 is an inflection point because there is a change in the inflection. Okay, so that's all it is. This was a fairly simple problem because our second derivative was so nice and easy to work with. So let's try a slightly more harder one where finding the derivatives is going to make us use a little bit more of our rules. So let's find the concave up and concave down intervals and any inflection points for the function 6 over x squared plus 3. So first we have to find our first derivative. So in order to do that, we could rewrite it and bring that x squared plus 3 quantity up using a negative exponent and then using our product rule, which I know a lot of people are more comfortable with. But let's use our quotient rule and keep it in this nice rational form because it'll make solving for our second derivative a little bit easier. So our quotient rule is always the derivative of the top. So the derivative of 6 is 0 times the bottom, so times x squared plus 3, minus the top, so 6 times the derivative of the bottom, which is just 2x, all over the bottom squared, which is going to give us x squared plus 3 squared. So now we just are going to clean it up a little bit before we go ahead and take our second derivative. So this first term here is all going to 0, and then negative 6 times 2x is going to give us a negative 12x in the numerator, all over that x squared plus 3 quantity squared in the bottom. Okay, so now let's use our quotient rule again to find the second derivative. So again, quotient rule starts off derivative of the top, so negative 12 times the derivative, times the bottom rather, so x squared plus 3 all squared, minus the top, so negative 12x, times the derivative of the bottom. So to do the derivative of the bottom of this x squared plus 3 all squared, we have to use our chain rule. So first we're going to bring down that exponent of 2, and then leave the base alone, so x squared plus 3, the new power of 1, times the derivative of the inside of this thing, so times 2x, all over the bottom squared again. So x squared plus 3 all squared again is going to give us x squared plus 3 to the 4th, using our exponent rules, multiplying those powers together. Okay, so now let's just clean it up so it makes it a little easier to solve when we set it equal to 0. So this negative 12 times x squared plus 3 squared, that can stay as it is, fix up that square. and then minus a negative 12, these are going to become positive when we multiply them together. So then let's just multiply these coefficients together. So we have 12 times 2, which is 24, times another 2, which is 48. So we have plus 48. And then we have x times x. So we're going to get plus 48x squared. And then we'll leave that x squared plus 3 quantity alone. And then all over x squared plus 3 to the fourth. Now, if you notice, every single term in the numerator has an x squared plus 3 term. And there's some x squareds plus 3's in the bottom, which means that they're a common term, and we can divide both of the terms in the numerator by x squared plus 3, and we can get our powers down a little bit. So this is actually going to become negative 12 times x squared plus 3, just one of them, plus 48x squared. I know that looks like an 8 there, but it really is a 2, times 1, because we can divide by that x squared plus 3 term. And when we do that, we can make this one on the bottom an x squared plus 3 all raised to the third power instead of the fourth. Okay, so now the next step in finding our concavity is to set this equal to 0 and solve. So now, because we have a rational function, we need to look to see if we are ever going to be undefined. So that means we need to look to see if x squared plus 3 all cubed is ever going to equal 0. Well, if we take the cube root of both sides to cancel that third power, we get x squared plus 3 equals 0. And then we would get x squared equals negative 3 if we move that 3 over to the left-hand side. But x squared is always positive, so we're never going to get a solution. So we're okay. There are never going to be any x values that make this thing undefined. So that means if we multiply both sides by x squared plus 3 all cubed to cancel with it in the denominator. So it'll cancel over here. That way we can just work with a singular line instead of a fraction. We're going to get 0 equals, now we can distribute this negative 12 into this quantity. So we're going to get minus 12x squared minus 36 plus 48x squared. If we simplify a little bit more, we're going to get 0 is equal to 36x squared minus 36. We can factor a 36 away from both of those terms then, so we're going to get 36 times x squared minus 1, dividing both sides by 36 to cancel with that coefficient. I'm going to cancel the 36 on this side. We're going to get 0 is just equal to x squared minus 1, which we know we can factor to be x plus 1 times x minus 1. And then we know we can set both of those equal to 0 and then solve for the individual x values, which is going to give us that x is equal to negative 1 and x is equal to positive 1. So we have two critical values this time. So these are both critical numbers. And now all we have to do is go through, pick some test values to put on our handy-dandy sign chart with the second derivative in the top and our x's in the bottom. So first let's put on our two critical values of negative 1 and 1, and note that there are 0 second derivatives. So now let's pick three test values. So picking one to the left of negative 1, we could pick negative 2. 0 is a nice number to pick in between negative 1 and 1. And then let's pick positive 2 over here on the right-hand side. Okay, so now we're going to do f double prime of negative 2 first. So let's scroll back up here and remember what our second derivative was. So we know that when we simplified the top of it, we got this thing here. So negative 12x squared minus 36 plus 48x squared, which came down to this thing. 36x squared minus 36. And that was all over x squared plus 3 cubed. So maybe we'll write it down here so it's easy to reference. Okay, so 36 times negative 2 squared is 36 times 4. Oops. Forgot the 6. So we have 36 times 4 minus 36 all over x squared, so 4 plus 3, so 7 cubed. Well, our bottom is positive, and our top is certainly going to be positive because 36 times 4 is certainly bigger than just a 36, which is going to give us a positive answer at the end. So like I've said before when we were doing the increasing and decreasing intervals, you don't actually always have to find the value of the first or second derivative. All you have to do is determine if it's going to be positive or negative, because that's all you're really interested in knowing. So if we plug 0 in, we're going to get 0 minus 36 in the top over 3 cubed in the bottom. Well, the bottom is certainly going to be positive, but 0 minus 36 is negative, so we're going to get a negative second derivative at 0. And then the second derivative at 2 is again going to be 36 times 4 minus 36 all over 7 cubed, which is again going to be a positive number. Put a positive sign above there. Okay, so now all we have to do is write our intervals and determine if we have any inflection points. So we are concave up for this function. It looks on two different intervals because we have two plus signs. Okay, so when we write the interval that's to the left of -1, we can write that as negative infinity to -1, union, that second interval goes from +1 out to positive infinity, and then we are concave down on the interval in between -1 and 1, so we can write that as -1 to 1. That's our only spot where we have a minus sign, so it's our only concave down interval. And then let's see if we have any inflection points. So it looks like we actually have two, because we have that we're positive and then negative, and then again we go from negative to positive. So we have two changes in the concavity, so we have two inflection points at x equaling -1 and x equaling 1. So there you go. There are two examples of how you go about finding the concavity of a function and the inflection points. So thank you so much for watching. Have a great rest of your day.